So we are to part 2 of chapter 14. So what we're going to look at in this video are how we mentioned in the last video that concentration of the reactants is one thing that can impact the rate. And we said very generally, the higher the concentration, the faster the reaction goes. The slower the concentration, the slower the reaction goes. But there are times we're going to want more detail than just that. We're going to want to know, well, what if I increased it, I doubled it? Well, what's that going to do to the rate? Well, we need some sort of mathematical relationship, some equation between those. So that's what we're going to focus on in this video. So again, we're focusing on how concentration impacts the rate. So if I do the same reaction a second time with different concentrations, what is the rate? So what we need to do is we're going to have to look at each reactant individually. So we will look at, usually we're going to have two reactants in our chemical reaction. We'll look at one and see how, if I do the experiment once and then I do the experiment a second time and the only thing that I changed was the molarity of one chemical, we can see what happens to the rate. And we know that any change to the rate came from that one chemical. And then we can use that information to come up with a relationship. Then we can do the experiment a third time, and that time keep the reactant 1 concentration the same as the first time I did the experiment and change the reactant 2 concentration only, and then see what happened to the rate then, and then come up with a relationship between those two. So again, for our examples, we're going to pretty much always have two reactants, so we'll have to do this twice, one for each chemical. So here's an example. This is the chemical reaction, the ammonium and nitrite, making nitrogen and water, that happened here. And what they did was they did the experiment 6 times. All 6 times they did it at 25 degrees Celsius, so that way the temperature was not changing between these. The only differences between these 6 experiments were what the molarities of the ammonium and the nitrite ions were when they started. So that's why we see our columns. They just numbered the experiments 1 through 6. Then they tell us what was the initial ammonium molarity, the initial nitrite molarity, and then they've already calculated the initial rate, which is the fastest rate for each experiment. So what we're going to have to do is we're going to have to look at each chemical separately, the ammonium and the nitrite. So if we're going to do ammonium first, what I'd like to do, if I want to see when I changed the ammonium molarity, it changed, and I want to know how much did it change the rate. Well, I need to have 2 experiments. I need to have one experiment that can just be my basic one, and then my second experiment will be exactly the same, except the ammonium molarity changed. So in other words, the nitrite molarity did not. I want the only change to be this when I'm looking at the 2 concentrations. So I'm looking for 2 experiments that are the same in their nitrite molarity and different in their ammonium molarity. Looking at that, experiments 1 and experiment 2 meet that criteria because the nitrite is the same, but the ammonium changed. Now, I know the rate changed. We're going to look at that here in a second. But what we were looking for is something where the only difference between the starting chemicals was the ammonium. So 1 and 2 would be an example of this. So would 2 and 3, or 1 and 3, because look, the nitrite molarity is the same in all of those. I'm going to pick 1 and 2. So what I did was I just took experiments 1 and 2 and put them up here. So what we're trying to do is we're trying to come up with a relationship where, I can know, well, whatever I do, so where it's, I guess I should be more generic. I want to know the concentration. If I double the concentration or whatever, that to what power will happen to the rate? So we're trying to figure out, well, if I double the concentration, will the rate also double? Or if I double the concentration, will the rate quadruple? Or if I double the concentration, will the rate go down by a factor of 2? That's what we're trying to figure out. So what we're solving for is this power right here. So what we need to do is we're going to look at the 2 experiments that we chose, and we're going to look at the rates and the concentrations for those 2 experiments. So for the rate, well, I'm going to take the 2 rates. I'm going to take big number divided by small number. I want to see by what factor, that's a 5, did the rate increase by. So I divided them by each other, big number divided by small number. Then I'm going to do that for the NH4 plus concentration as well. So it looks like I doubled the molarity of the ammonium and the rate doubled. So what we're trying to do is put that into this relationship that I have up here. So for rate, I'm going to plug in 2 rate. For concentration of ammonium, I'm going to plug in 2 right there. And then what I don't know is that power. So 2 to what power gives me 2? Well, 2 to the first power gives me 2. Okay. So this is, I just have a relationship between ammonium and the rate. So if I doubled the ammonium, 2 to the first power, well, which is 2, is going to happen to the rate, which is also 2. So what if I tripled the molarity? So if the concentration was a 3, well, 3 to the first power is 3, so the rate would also triple. If I took the concentration times 5, well, 5 to the first power, the rate would go up by a factor of 5. That's what this lets me do. So knowing that power, which we're going to call them orders, actually it's first order, is what ammonium is. So we know ammonium raised to the first power is how it's related to the rate. So what we want to do, that's what we just did. Okay. I went back to the original table, and now I want to redo this, but for nitrite. So we want to know, okay, when nitrite changes, when the molarity of nitrite changes, what happens to the rate from that? So what we're looking for now are 2 experiments where the nitrite molarity changes and then the other chemical stays the same. So the only thing that's changing is the nitrite. Well, when we look at this, well, it could be 4, 5, 6. All 3 of those have ammonium the same and nitrite different. So you could choose 4 and 5. You could choose 5 and 6. You could choose 4 and 6. It doesn't matter, but you're going to have to choose 2 experiments where the NO2 minus changes. And again, the one that changes, that's the one we're looking at. And then the other chemical stays the same. Because if they're both changing, there's too many things happening. We don't know why the rate changed. Okay, so I'm going to pick 4 and 5. So I just took 4 and 5 and rewrote those. So what we're looking for is, again, a relationship where rate is equal to the concentration raised to some power. And this time it's going to be rate is equal to the nitrite to some power. So I'm going to take the rates. We're going to see by what factor did it change. So it went up by a factor of 2. And then we're going to look at the nitrite. Again, when I'm doing my dividing, I'm taking big number divided by small number. So the rate is 2. The nitrite is 2. 2 to what power equals 2? Well, this is also 1, which means nitrite is also first order. So if I tripled the NO2 minus, the rate would triple. If I took the NO2 minus times 12, the rate would go up times 12, is what we're saying. We're seeing a relationship, a mathematical relationship between these. Okay, so that's what we just saw. I just put the actual numbers in here. So we used the first experiment 1 and 2 to look at NH4+. We looked at experiments 4 and 5 to look at NO2 minus. We need to put it all together. Putting it all together is called the rate law. And this is what the rate law looks like. It will always look like this. Rate equals K, and then in brackets is reactant 1, the first reactant, raised to some power, times reactant 2 raised to some power. Now, if we have a catalyst, catalysts can also be included in the rate law. So we could have a reactant 1 raised to some power, a reactant 2 raised to some power, and then a catalyst raised to some power. Okay. So in this experiment, the NH4+ and the NO2- were my reactants. I got that from the balanced chemical equation. The powers, those came from what I just did. I got a 1 when I looked at NH4+, and I got a 1 when I looked at NO2-. So this is the rate law. It's the mathematical relationship comparing the rate to the molarities. So the only way to get these powers, the number that goes here and here, is to do what we just did, looking at a set of experiments and choosing 2 experiments and comparing them. Now, lowercase k is called the rate constant. Now, it's not a constant like the ideal gas law constant. That's always the same number all the time. That constant has, the number varies, the unit varies, So it varies. It's not even the same all the time. And it changes based on temperature and the reaction. So like this reaction, NH4 plus and NO2 minus. At 25 degrees Celsius, it has a specific value that's the rate constant. Now when I change the temperature to 35 degrees Celsius, the rate constant changes. Now when I do a different experiment involving N2 and H2O, don't do anything, but that's okay. At 35 degrees Celsius, I have a different value. So every time we change chemicals and change temperatures, the rate constant changes. But the rate law is going to be an important mathematical relationship for us to come up with. Okay. So the exponents are called the order. So if the exponent is 1, it's the first order. If the exponent was 2, it would be second order. The exponent could be 0, which would be 0 order. Okay. So reactant 1 is first order. Reactant 2 is first order. So the overall reaction is second order. Because if this is 1, oh, pen. Be my friend, pen. There we go. If this is 1, nope, still not friends. Okay, so if this is 1 and this is 1, then the reaction, which is the total, is the really complicated math of adding all the orders together to get the total. So the overall reaction order is 2 because one chemical is first order, the other chemical is first order. So together, they're second order. Okay. So again, K is the rate constant. It is temperature dependent. So if we do the same reaction again, but at a different temperature, we get a different number. And then every reaction is obviously, it has its own unique rate constant as well. So for a generic equation, this is what a rate law is going to look like. Rate is equal to rate constant times reactant 1 to some power times reactant 2 to some power. Now notice, M and N are not the same as the coefficients. We don't know what the orders will be from the balanced chemical equation. We're going to have to look at a set of experiments, just like we just did. If there was a faster way to do this, I would tell you, my friends, but this is it. So in order to figure out the reactant order, the order of each reactant, we have to be given a set of experiments that someone has already done and compare those experiments. So this is just pointing out that the order and the coefficient are not necessarily the same. So like in this one, the rate law is rate equals K times N2O5, and then there would be a 1 there. There's a 2 in front of it. So they're different. Okay, that's what I mean. This time, there's a 1 in front of H2, there's a 1 in front of I2, and both of them are first order. Huh. All right. Well, for this one, CHCl3 has a 1 in front of it, and there's a 1 right there. Cl2 has a 1 in front of it, there's a half right there. So all I was trying to point out is you have to look at the experiments. You do not know the order just by looking at the balanced chemical equation. So what we haven't done yet is solving for the rate constant. Okay, so I just took the rate law from our previous example, and here's the data table from our previous example, and what I want us to do is solve for K. So this is a mathematical equation, which means I can treat K like an unknown variable, plop in a rate, plop in an NH4 plus molarity, plop in an NO2 minus molarity, and just solve for K. So to do that, you're just going to pick one of the 6 experiments. I always pick experiment 1, just because I'm afraid if I go further down the table, I'm not going to read straight across the table, which is a silly fear. But anyway, that's the experiment that I'm going to go with. And what I'm going to do is I'm going to take the rate from experiment 1, put it in the rate spot. Put the nitrite number for experiment 1, put it in the nitrite spot. Put the ammonium number, put it in the ammonium spot. And then solve for K. So that's where these numbers came from. Now, number-wise, I'm not really worried about you doing this math. So we got 2.7 times 10 to the negative 4th. Units are what we need to talk about, though. Okay, so if we look at this, and I'm going to focus on units. This is molarity per second on the top, and this is molarity times molarity. I'm going to write molarity squared. Now, when I go to cancel out units, well, I can cancel out one of the molarities. That's a 1 now. So what I have left is 1 divided by seconds, and 1 divided by molarity. And they're times each other. So I could write 1 over molarity times seconds, or 1 over seconds times molarity, or I think it looks neater if you write molarity -1, seconds -1, or seconds -1, molarity -1. The units on the rate constant There will be some. There will be units, and they're not going to always be the same. It's going to depend on what these orders are, because if this had been a 1 and this had been a 2, then I would have had to square my molarity unit, which would have changed my final answer. So the rate constant has a different number every time, has a different unit every time. Okay. So let's try this again. Oh, this was just me giving you some examples of the units on rate constants here. But there's not just 0 or first and second order overall. I don't think it's worth memorizing these. You just solve for them. Okay. So here's another experiment. There's the balance equation. Then I did 5 experiments, and I'm giving you that information. Based on this information, we need to figure out the relationship between hydrogen and the rate. So we need to figure out the order between hydrogen and the rate. We need to figure out which experiments we should look at when we're comparing hydrogen. Then we need to look at NO and the rate and figure out which 2 experiments we should compare for NO. Then I want you to write the rate law and then solve for K. So what I would like you to do is hit pause and try to do those 4 things. Choose your experiments and find the order for hydrogen. Choose your experiments and find the order for nitrogen monoxide. Write it as a rate law and then solve for K. Once you're finished, hit play and we'll go through this together. So for hydrogen, if I'm choosing my experiments, what I'm looking for hydrogen are 2 experiments where the hydrogen molarity changes, but the nitrogen monoxide molarity does not. So what I want to change is just the hydrogen number. So I could choose 1 and 2, or I could choose 1 and 4, or I could choose 2 and 4. So any combination of 1, 2, 4. So 1 and 2, 1 and 4, 2 and 4. I'm going to do 1 and 2. Okay. So that's for hydrogen. So for hydrogen, it's going to be 1 and 2. So I guess actually before we go on, I want to do it for nitrogen monoxide as well. So when we're looking at nitrogen monoxide, I want to pick which 2 experiments I should look at when I'm comparing nitrogen monoxide. And in that case, I'm looking for NO's number to change and hydrogen's number to stay the same. Well, it looks like I could do 2 and 3 or 1 and 5. Okay, either one of those are going to work. So, oops, I got rid of my blue. I didn't mean to do that. What I want us to do is let's look at hydrogen first, and I'm going to choose experiments 1 and experiments 2. So for hydrogen, I'm looking at experiment 1 and 2. So I'm looking at hydrogen. Looking at hydrogen, I'm looking at the rate. What I want to know is the relationship between rate equals hydrogen to some power. So experiments 1 and 2. So for hydrogen, I did, oops, zooming in. Oops, still zoomed in. So hydrogen's experiment 1 and 2, big number divided by small number. Okay, and then for rate, 8.40 times 10 to the negative 5th divided by 2.80 times 10 to the negative 5th, and I get 3. So for rate, I'm going to put in a 3. For hydrogen, I'm going to put in a 3. 3 to what power gives me 3? Well, 1. So hydrogen is going to be first order. Now, if we had looked at experiments 1 and 4, so if we had done this one and this one, well, if I'm just kind of eyeballing this, 0.0300 divided by 0.02 or 0.0150, that would be a factor of 2. And then this divided by that is a 2. So 2 equals 2 to what power? I would still get first order. Okay, so I'm going to move on to the other chemical. I'm going to look at NO. And we had decided, or I think I had decided, 2 and 3. Although I could have done 1 and 5. Which, looking back, I think I said 1 and 4 in the last one, but it would have been 1 and 5 for this. I'm going to do 2 and 3. So I'm going to look at NO. I'm going to look at the rate. So for NO, 0.0300 divided by 0.0150, I get a factor of 2. And then for the rate, I get 3.36 times 10 to the negative 4th. Notice that is the bigger number because it's to the negative 4th. Then 8.40 times 10 to the negative fifth, and when I do that, I get a 4. So I'm trying to come up with the rate equals NO to some power. So for rate, I'm putting a 4. For NO, I'm putting a 2. So 2 to what power equals 4? Well, it's not 1 this time. 2. 2 squared equals 4. So this is going to be second order. This was first order. That was second order. So what do you think the overall order is going to be? Well, third, 2 plus 1. Okay. So the rate law, I'm just putting all this together. Rate equals K times chemical to the power, chemical to the power. So K times NO, second order, H2, first order. And if you had written it, hydrogen, first order, NO, second order, perfect, awesome, wonderful, it's the same thing. Okay. Now I want us to calculate for K. So what I'm going to do is just choose experiment 1, there, these numbers, and I'm going to substitute those numbers into my rate law. So for rate, I'm going to put 2.80 times 10 to the negative 5th molarity per second. K is my unknown. NO is 0.0150 molarity, and I need to square that. And then hydrogen is 0.0150 molarity, and that's raised to the first power. Okay. So number-wise, for K, I got 8.30. Now let's look at the math. So to get K by itself, we would take molarity per second, which is on the left, divided by, well, molarity squared times molarity, which is the same as molarity cubed. So I can cancel out 1 molarity. So I'm going to have molarity negative 2, seconds negative 1, or 1 over molarity squared times seconds, or 1 over seconds times molarity squared, or seconds negative 1, molarity negative 2. All 4 of those units are correct. So this is definitely going to be a thing you're going to be tested over. You're going to recognize these problems because I'm going to be giving you a table with a bunch of experiments and asking you to write the rate law and then solve for K. I'm probably going to ask, like part A, what's the order of NO? If this was a test question. Part B, what's the order of H2? Part C, what's the overall order, which would be 3 this time. Part D, write the rate law. Part E, solve for the rate constant, including units. That's how these questions are going to go.